Welcome to this movie on statistical mechanics. My name is Jos Thijssen and I teach statistical mechanics at the Delft University of Technology to students in the Master Applied Physics program. This movie is a follow-up movie on a previous movie. The previous movie is called the Langevin equation, fluctuations in the Langevin equation, and there I focused on the velocity of particles that are subject to many collisions of much lighter particles. In this movie I'm taking another step, and instead of looking at the velocities I'm looking at the displacement of the particles. And it turns out that the displacement of these particles is described as a random walk, and I will study extensively the random walks, the diffusion equation, and also diffusion in the presence of a drift force, for which I will derive the Einstein-Schmolukowski equation. I hope you enjoy this movie. The previous movie started from the Langevin equation, which I have repeated here. It's mv dot is minus gamma v plus rt. Minus gamma v is a frictional force, rt is a random force, that's the Langevin force. And this describes how heavy particles experience kicks from lighter particles and thereby change their direction. Now that reminds us obviously of random walks where particles take arbitrary steps in arbitrary directions and of arbitrary size often. And we know that for random walks, the displacement squared, if we take the average over many walks, so in this case that would be the average over many realizations of the random force, if we take that for long times, then it should be proportional to 2dt. The time doesn't really have to go to infinity, but here I only want to denote the fact that the time is long. For long times, we find that the displacement squared on average is proportional to t. That's in contrast to ballistic motion, where the displacement itself is proportional to t. Now the aim of this movie is to start with the Langevin equation and its solution for the velocity, and from there integrate again and then find the displacement and reproduce this behavior, this law, this diffusion behavior. And in particular, we want to relate this number d to the constants occurring in this equation. That's first of all the frictional constant, and second of all that's the amplitude of this r, which in the previous movie we have denoted by the symbol q. We have been dealing with particle moving under the influence of other particles, and so the motion of the particle under consideration can be characterized as a random walk. And for random walks there is a very famous result which tells us that the displacement squared after long times is equal to 2d times t, where d is a constant. It's called the diffusion constant. So from the Langevin equation that we have analyzed, could we infer that indeed this is the behavior? That's question number one. And the second question obviously is, what would be this diffusion constant? So we try to find x squared t, but so far we have been dealing only with the velocity. Now there is a simple relation between the x and the velocity, just the time integral over v, and we can use the known solution for v from the Langevin equation in order to make some statements about the x. Recall that the solution for the velocity that we have found above for the Langevin equation had this form. First we have a homogeneous solution, and then we have to add a particular solution which depends on this random force r. So what we could do is take this v, plug it in there, and then calculate x squared, and then take the expectation value. That's quite a bit of work, and therefore we take a shortcut. This shortcut starts by writing up the equation of motion not in terms of v, but in terms of the x. So we get mx dot is minus gamma x dot, that's the drag, plus the random force. We multiply this equation on the left and right hand side by x, And then we will take the expectation value. But let's first do this. So we calculate x times x dot dot. And my claim is that we can write this as the time derivative of x times x dot minus x dot squared. Because if I work out this, I get two terms. One is this term and the other one is that term. So in order to get that term, I need to subtract this velocity squared term. M times the velocity squared is twice the kinetic energy, can be related to kBt, equipartition theorem, and then we obtain the following equation. I've moved the term with the minus gamma to the left hand side and the kinetic energy to the right hand side and replaced it by the constant kBt. And then here we have an RT times an XT. Then we take the expectation value everywhere and recall that taking the expectation value means averaging over all the possible realizations of the random force. So here we have just an expectation value of x times x dot. Here we have the same expectation value. Here is a constant, so the expectation value has no effect. And here we have the expectation value of the random force times x. But the random force itself is completely independent of x, whether the particle is here or there. It will not have any effect on the random force, and therefore it's uncorrelated from x. So this, we can put the x outside of the expectation value, and then we find just the average value of the random force r, and we have already seen several times that that is equal to 0, so this term disappears from the equation. And so we have now an equation in terms of the expectation value of x times x dot, which we can call, for example, y. The solution can easily be found. It's a straightforward differential equation, and it reads c plus a times e to the power minus gamma t over m, where c and a are constants. C is not an arbitrary constant, but if I plug the solution into the equation, I see that it must be equal to kBt over gamma. And therefore, if we take the time to infinity, then I'm left with just c, and that's kBt over gamma for this quantity here. If the time is taken at 0, then obviously this quantity should be 0, because x is the displacement from 0, from its position at 0. And from that I find that also the a is minus kBt over gamma. And it's important to note that we can write x dot as half times the time derivative of x squared. This implies that we need to integrate once more in order to find x squared itself. This is the derivative of x squared. And if we then perform the integral, we arrive at the following expression: 2 kBt over gamma times t plus 2 kBt over gamma m over gamma e to the power minus gamma t over m minus 1. Let us first find the short time behavior for x squared. So we are looking at short times, which means that we can Taylor expand this exponential here, and I've Taylor expanded here to second order. And it turns out that the term with t here is cancelled by the first order term here. The 0th order term is cancelled by the minus 1. And so I'm left with a term that scales with t squared. And this indicates that for very short time scales, and that short means that t is a lot smaller than m over gamma, we have ballistic motion, because the displacement itself is proportional to t, so the displacement squared is proportional to t squared. And that's just the motion of a free particle. And that tells us that the collisions have not yet shown their effect if the t is smaller than m over gamma. When the collisions come into effect, then we cross over to a different behavior. For large times, we can calculate the x squared too, and in that case let us go back to the original equation. Then the exponential will decay, and so we are left with this term and a term with a 1, but when t is large, this term will be much larger than that term, so we can safely neglect the minus 1. And what we then find is that we have 2kt over gamma times t. And so that's 2 times the diffusion coefficients times t. And so what we find is that d is kBt over gamma. We have to express the diffusion constant in terms of the temperature and the friction coefficient, the drag. This gamma, there is a hydrodynamic equation for that. It's given as 6 times pi times eta times A, where eta is the hydrodynamic viscosity and A is the particle radius. So that's the radius of a particle. So if we have a large particle moving in a fluid and the particle has radius A, then it will experience a drag, which is given by this formula. This result is known as Stokes' law. When we were analyzing the Langevin equation for V, we also were interested in finding the probability distribution for V as a function of t. Now we have moved to the analysis of X, so it's natural to look at a probability distribution for finding a particle at position X, and that means that obviously pxt times dx is the probability to find a particle inside the small interval dx running from x to x plus dx at time t, so it's a time-dependent probability. Now we can make the following statement. V, as we have seen, is linear in R. Now x is the integral of V, so x is linear in V, and therefore x is also linear in R. Now RT has a Gaussian distribution, and because x is linear in R, xt is also a Gaussian distribution, because if we have a Gaussian distribution, consider for example e to the power minus alpha x squared, then if I change x by ax plus b, that will be also a Gaussian distribution. Any linear transformation leaves the Gaussian character of the distribution invariant. Now we have calculated before that the width of this Gaussian was 2 times d times t. That was the diffusion law. So the probability to make a step dx squared scales linearly with the time t, 2 dt. And therefore the transition probability, I call that t, and so it's a probability to make a step of size delta x within a time interval t. So I call this the transition probability. That should therefore be a Gaussian, because we know that the average of a step, of a random step, is 0. It should be a Gaussian, and the width of the Gaussian is known, so we can immediately write it up. And so we see that it also contains a normalization factor. There's just a normalization factor, which is induced by this term in the denominator of the exponent. Now, having this transition probability, we can write up an equation which gives us the evolution of this probability distribution P. So we start from a distribution at time t, and we want to make a statement about the distribution at t plus delta t. So if at a later time t plus delta t we are at position x, then at the previous time t we were at a position x minus delta x, and the probability to go from this situation to that situation is given by the probability to make a step of size delta x, and that's this t that we have just found here, the Gaussian probability distribution. And because the delta x is supposed to be small, if the time here delta t is also small, it's natural to make a Taylor expansion, and we can do that straightforwardly. So here we take first the delta x 0, so we get the p at x at t. So this is the situation where the particle does not move at all, because it was at x at time t, and it's at x also at t plus delta t. Then we have the first order term, where we have a first derivative of the p and a second order term with a factor of 1/2. And here is the t. I've left out the t dependence from the capital T. And if we then calculate the integral, we see that if I multiply delta x, here is no delta x dependence, but if we multiply that by the symmetric Gaussian distribution t and we integrate over x, then due to the antisymmetry of the integral, this term will give 0. And so in the end, I'm left with this, where the delta x squared is the second moment of this distribution, and we know what that is. We can infer that directly from the Gaussian distribution. That distribution had a width of 2 times d times delta t, and because of the factor of 1/2, we find now this equation. Then we have here, if we move this one to the left-hand side, we see that it can be written as the first order time derivative times delta t, and then we obtain the following equation. We have dp dt, partial derivative with respect to t, is d times d squared p dx squared. And it's important to note here that this equation, it's called the diffusion equation, but it's only valid if the d is constant, so the d does not depend on x, so d constant. It's also possible to derive an equation for a non-constant d. In that case, there is also a x dependence in the t, so that has to be taken into account when Taylor expanding the terms here in the integral, and in that case what you find is d dx, and then we have a x dependent diffusion constant dp dx, where the p depends on x and t, so that's general. It's important to emphasize the assumptions that we have made so far. First of all, we have assumed that we are in the diffusive limit, and that is justified provided that the time step is larger than m over gamma, because otherwise we are in the ballistic regime still. On the other hand, we have made a Taylor expansion, and that is justified only when the delta x is small, so the transition step should be small. Well, looking at the distribution, it means that this delta x is a lot smaller than dt. Delta x squared should be a lot smaller than dt, and that is justified if the time is long enough. Now we move to an alternative derivation of the diffusion equation, which is via Fick's law. And Fick's law tells us that the flux of particles through some area, surface area, is equal to rho, that's the density of the particles, times their velocity. So I have here a small surface area A, and the flux is just the number of particles passing through A, and I calculate that I divide it by A, so I calculate it per unit area, and I calculate it per delta t, so these are the number of particles passing through A in time delta t. Of course, if I wait twice as long, I will have twice as many particles, so dividing by delta t makes it independent of this delta t, and the same holds for the area. If I double the area, I have twice as many particles passing through it. And Fick's law tells us that the flux through this area is given as the density of the particles, just the number of particles per volume, times their velocity, times their average velocity. And I will now derive that law in some detail. I consider the diffusion of particles along a one-dimensional axis, that's the x-axis, and we have a point x is 0, and we look at the flux. We want to calculate the flux through this point x is 0, and therefore we consider particles which at some time started off at a position x0, which is smaller than 0, and these particles are traveling during some time delta t, and initially they were definitely located at this position, but they will form a Gaussian distribution after some time, and so therefore we will have this Gaussian distribution expressing the distribution of the particles after some time delta t, which is obviously positive. And if you want to calculate the flux through x0, that's just the number of particles which have passed the point x0, and they are the particles which are on the right tail of the Gaussian. And therefore we can write up immediately an expression for the flux through x0 due to the particles coming from x0. Here is that expression. We have a Gaussian distribution, and I integrate only the part for the positive x's, and the x0, which occurs here as the center of the Gaussian, should be negative. So we have an x0 smaller than 0. And I can do the same for particles released at the positive x-axis. The blue Gaussian curve is centered at an x0 which is positive, and the particles which have contributed to the flux through the point x0 are the ones that I find in the left tail of the Gaussian distribution. And therefore the mathematical expression for this is the following. So we have for particles coming from the right the integral which is given here. It's the green shaded part in this picture. And now in order to derive the diffusion equation, we assume that at some time we had a distribution of particles which is given by rho of x. Each of those particles can diffuse according to these evolutions, and therefore we multiply this by rho at x0 and we integrate over rho x0, and that's the flux of particles passing to the right of x0. We do the same for this one. We multiply it by rho of x0, and then we integrate over all the x0s, and that is the contribution to the flux to the left. The flux to the right has a positive sign, the flux to the left has a negative sign, so we need to subtract this integral then from that integral, and this results in the following. We take the first expression, x0 being negative, and we integrate over all the possible positions. Here we multiply that by the density of particles at that position at time t, and then we wait for some time delta t, and then these particles are distributed according to the black curve, and this integral then calculates the red area for each of the particles starting off from the left. And down here we have the same expression, but then for x0 positive, and it has a minus sign because we are calculating now flux for particles going to the left. The rightmost integral can be reworked because we can swap the two boundaries of the integral. We can also change their sign, then nothing changes in the overall sign, so I still have a minus, and I have now an integral from minus infinity to 0 over dx0 and the integral over dx. I do the same for that one. I have a 0 to infinity. Nothing changes here because both x and x0 have changed sign, but there is a difference in the rho, which is here, here it depends on x0, and because I've swapped the sign of the integration variable, this is now rho of minus x0t. Also, since we shall be interested in short times, we expect the particles contributing to the flux to be located very close to x0. It is natural to make a Taylor expansion for rho as a function of x0. So we write that rho x0t is rho of 0t plus x0 times rho primed. And with rho primed I mean the derivative with respect to the first argument, so with respect to the x. And this assumption then simplifies this long expression here. First of all, we see that if I take rho 0t, that term is the same for this one and that one. And then we see that the two integrals are completely identical, except that they have a different sign, so they cancel. And so we should have a look at this one, because here we have a term with a plus sign here and a minus sign there. And therefore the result is the following. Here is the resulting expression, which has a factor of 2, because I have the same contribution for the first term as I have for the second term, however with a different sign, because the x0 has turned into a minus x0 there. And together with this minus sign I have a factor of 2. Then I can extract this term rho primed 0t in front of the integrals, and I have here an x0 which is negative. The integrand apart from that is positive, and so therefore I have a negative result. I have in fact minus rho primed 0t times the diffusion constant times delta t. Performing the integral is a little bit tricky, but it is in fact straightforward. So this is the result, and this is Fick's law of diffusion, or this expresses Fick's law of diffusion. What we have calculated is the amount of particles which during a period delta t flow through x0. And it's in fact it was the net flow of particles, because we took the particles moving to the right with a plus sign and those moving to the left with a minus sign. So by definition this is also j times delta t, and j is then calculated at x0, so it's the flux that we have calculated at x is 0. But of course there is nothing special about the point that we have taken. We have now taken the point x is 0. We could have taken any point, and therefore we have in general that the flux j as a function of x and t is d times, with a minus sign, the derivative of rho with respect to x at x and t. This is the one-dimensional version. It can be generalized to more dimensions, and then it reads jr of t is minus d times the gradient of rho r of t. And this is the famous Fick's law of diffusion. And what it tells us is the following. If you have a variation in the concentration of particles, the flux is always such that it tries to even out the distribution of the particles. So it always tries to flatten the particle density. Fick's first law, which gives us the diffusive current, is not yet the diffusion equation. In order to derive the diffusion equation, we need to combine this with a different law, which tells us something about the conservation of particles. So we consider a volume of V, which is bounded by a surface A, and we consider this change in the amount of particles inside V. So how does that change in the course of time? Well, the total amount of particles is the integral of the particle density over the volume, and if we compare that for t and t plus delta t, we have this expression. So this expresses the change in the amount of particles inside V. If we realize how the number of particles can change, we conclude that this can only change by particles passing through the surface area A and the flux of those particles is J, so we have to integrate that over the surface area, and that is per unit time. So if we have a delta T here, we need to multiply this by delta T. What is important in writing up the right-hand side is that we neglect the effects where a particle, or the processes in which a particle could just disappear into a sink, or it could just appear from a source. So there are no sources or sinks. So only particles moving through the surface can change the total number of particles inside the volume. We then note that the left-hand side can be written as the derivative of rho with respect to t times delta t. That delta t cancels against this delta t, so we have then that the derivative of rho with respect to dt is equal to minus j dot dA. And for that last expression we use the divergence theorem in order to convert the surface integral into a volume integral at the price of putting a divergence in front of the j. And if this should hold for any possible volume, so this should hold for any volume that we can think of, then we obviously have that d rho dt is minus a divergence of j. So we have d rho dt is minus divergence of j, and that expresses in fact the conservation of matter, and it's called the continuity equation. Combining the continuity equation with Fick's first law, so we use that J diffusion is minus d times gradient of rho, we plug that in, we immediately obtain the diffusion equation, and we have arrived at a similar equation before, but that was in terms of p, the probability to find a particle at a certain position, and obviously these two are strongly related. Rho is proportional to p, and so you see that if you plug in p, the probability to find a particle somewhere, then that also satisfies the diffusion equation, which we have now derived in two ways. The way that we have just seen was using Fick's law that we derived first in quite some detail. We combined it with the continuity equation, and before we had used a different approach, and that was for the probability. And that was from a time evolution of the probability. But in both cases, the assumption that was the fact that that x satisfies a Gaussian distribution probability if we release a particle from a particular position for some time. So far we have considered diffusion in the absence of a systematic force. So the Langevin equation contained just the drag and the random force. Now we introduce the systematic force once again, and for a physical picture you could think of gravity. Particles are dragged towards the bottom of the system, or you could think of an electric field which pushes particles that have a charge in one direction. And in order to make progress, we will now assume, for simplicity, that this force F is constant in time and does not depend on the position. If we assume F to be constant, we can consider the situation in which the velocity is stationary. In that case, the time derivative of the average velocity should be 0, and from the right hand side we see then that minus gamma v plus F should be 0. If the force is absent, the average velocity is 0, but if the force is there and it's constant, then we will find a constant velocity and therefore a constant flux, which is induced by this drift force. So that's the drift flux, Jf. And what happens if the system is closed is that if the particles move towards one direction, they will heap up at one side of the system. So for example, if I have a container and I drive all the particles to the right, then they will heap up towards the right wall. And so because there is now a strong slope in the density of the particles, there will be a flux which counteracts the drift force. So, and that's the diffusion flux. So if in the end we will reach a situation in which the drift flux is balanced by the diffusive flux, and then obviously the particles don't move anymore. And if we have that balance, we have the following equation. The gradient of rho divided by rho is F over gamma d. And so we generalize this result now to forces that really depend on the position, because then you can maintain the same argument in the end. If the force does not depend on time, but it depends on position, this flux will depend on position, but in the end you will have a diffusive flux, which is also depending on position, and we will have this balance equation which leads to this final result. Now it's useful to write this force as the gradient of a potential. So here we see gradient potential divided by gamma d, and we can rewrite the left hand side as the gradient of the logarithm of rho, and that enables us to write up the solution right away. The solution is then given directly as a constant times e to the power minus u over gamma d, and that is the distribution that we find in equilibrium. But on the other hand, we know that in equilibrium this should be the Boltzmann distribution, so it should be a constant times e to the power minus u over kt. And therefore we see that gamma times d is kBt. That is the same result as we obtained already before. So the diffusion constant together with the drag can be related to kt. Now we want to generalize the diffusion equation to the case where there are drift forces present. And what we have just seen is that if we have a time step that is long enough, we will reach a particular velocity, and that velocity is given by this equation. It's gamma average velocity of v is equal to the drift force. And if we use that, we can relate an old position to the new position, and we do that as follows. We start from an old position, which is x primed. We are going to a new position, x. And from the equation of motion, well, first of all, we get a term which is proportional to the velocity. So we have plus velocity times delta t, but the velocity can be replaced by f over gamma. So we have f over gamma times delta t. And then there is an additional Gaussian random step, and we call that delta x. So delta x satisfies a Gaussian distribution, and the time needs to be long enough to justify this second term. The delta t must not be extremely small. We try to formulate an equation for a probability p. Its probability density for the particle to be at position x at time t. And in fact we want to predict what this equation will look like at a slightly later time, starting from a distribution that we had at time t. And at time t we were obviously at a different position, that was x primed. We had a certain probability to be at x primed, and from any x primed in principle we can move to this. So first thing we need here is an integral over the dx primed. And then we should go to the new position x, so this is the new position, and because of this equation we therefore need a delta function, and that delta function reads as follows. It's x minus x primed minus f over gamma delta t minus delta x. And then we have a probability to make a step indeed of size delta x during the interval delta t. And we must realize that we should not only integrate over the initial positions, those are the x primes, we should also integrate over the steps delta x We can make every possible step, and the delta function will ensure that we end up at the right new position, which is x. So we have to add an integral over d delta x, and then we can later resolve one of the integrals using the delta function. What is important is that we integrate over delta x, and we have a distribution t, and what we will need when we later on Taylor expand are two moments of the delta x. Those are the average values first of delta x with respect to this distribution t, and because that distribution is assumed to be symmetric, the average step will be 0. There are equal probabilities to make a step to the left as to the right. And we also need the second moment, and if we assume that the delta t, the time step, is long enough for us to guarantee that we are in the diffusion regime during that time step, at the end of that time step, then we can write this as 2 times d times delta t. So these are two relations, these are two expectation values that we will need later on in the analysis. Now we want to carry out the integral over x primed using this delta function, but then we should realize that there is not only an x primed dependence here, but we can also take the force to be position dependent, and if we use an explicit expression for the integration, then this f is a function of x primed. Of course, we could also take it to be a function of x, but then the equation becomes more cumbersome. So you can choose to take either the force at the beginning of the time step or at the end, and we take it here at the beginning. Well, in view of that x primed dependence, when we resolve the delta function, we should divide by the derivative of its argument with respect to x primed. And that means that in the next line we first have 1 over that derivative. Well, first there is here an x primed, so that gives me an x, a 1. And then in addition we have here this delta, this f of x, so we have a 1 plus an f primed, or a df dx primed, times delta t over gamma. And now we can substitute in this integral for the x primed the value x minus f over gamma delta t minus delta x, because we use the delta function there, and obviously I should also allow for the t dependence. And then we have a t depending on delta x and delta t, and then we are only left with the integral over delta x, because we have carried out the integral over the x primed using the delta function. Then we take two steps. The first one is that we replace 1 over 1 plus this small number by 1 minus that small number. And the second thing we do is that we take the p and now Taylor expand it around this value or x, realizing that these numbers here are small with respect to the variation that we have in this distribution. So this is the first order Taylor expansion, and this is the second order term in the Taylor expansion, and then we are still left with the t. And now you see that we have a term here linear in delta x multiplied by t, and we also have a term which is square in the delta x also multiplied by t. So those terms give us the first and second moment. We call that what was the result of our expression was px at a slightly later time, and we evaluate that from this term. And we first consider the terms that do not depend on delta x. There is no delta x in the integral. So an example is this term, then we have just the integral over t taken over the delta x. So that gives me a 1. So I have a p first, and then I have a minus df dx times delta t over gamma multiplied by the same p. Then we have a term f over gamma times delta t times dp dx. That's multiplied by this 1. So that is here. And this term obviously doesn't count because that would give, in combination with this term, a delta t squared. Finally, we have here again a term which is proportional to delta t squared, so we neglect all the terms that are proportional to delta t squared. Furthermore, the terms which have in the integral a linear dependence on delta x, they all vanish because the first moment of delta x with respect to this t vanished. And so then we only have to add the second order terms. So here there is a delta x squared, and we know what the result of that integral is over t with t over delta x. And so we obtain then a half times d squared p dx squared, and then 2d times delta t. And considering the difference between these two, that can be written as a time derivative of the p, a partial derivative with respect to time, multiplied by delta t on the left hand side, and I divide out the delta t on the left and the right hand side, we see that we arrive at the following equation. We first have a minus. I can combine these two terms because I have a derivative with respect to of f with respect to x times p, plus a derivative of p with respect to x times f, so that can be written as d dx p times f, and then there is a gamma here in the denominator, which does not depend on x. And then the second term simply gives us a d times d squared p dx squared. If we would not have this first term here on the right hand side, we would have an ordinary diffusion equation, and we see that it's this term which accounts for the drift force, and the equation that we have now obtained is called the Einstein-Schmolukowski equation. It is also called the drift diffusion equation.